Hello students, in this video we will see how to find complementary function when we have complex roots. So in last videos we have seen methods to find complementary function. So first, this is our nth order linear differential equation with constant coefficient. First step is we consider homogeneous equation by putting this f of x is equal to 0. Then we use this notation d by dx is equal to uppercase D. So we got this polynomial in D operating on y is equal to 0. Then we find auxiliary equation, so which is this m raised to n plus a1 m raised to n minus 1 up to an is equal to 0. So this is how we get auxiliary equation. The next step, you find roots of this auxiliary equation. So if these are the roots m1 m2 up to mn, so this will have exactly n roots. Then we find a complementary function, which is this yc is equal to c1 e raised to m1x plus c2 e raised to m2x and so on up to cn m raised e raised to mnx, provided all these roots are distinct. When roots are distinct, this is yc, and when roots are repeated, suppose here this m1 and m2 are equal, that means m1 repeated 2 times and all other roots are distinct. In that case, complementary function is this yc is equal to c1 plus c2x into e raised to m1x plus c3 e raised to m3x and so on up to cn e raised to mnx. This is when one root repeated twice. If two roots repeated twice, for example m1 is equal to m2 and m3 is equal to m4, in that case complementary function is this yc is equal to c1 plus c2x e raised to m1x because m1 repeated 2 times, c3 plus c4x into e raised to m3x because m3 also repeated 2 times, and for all other roots single terms. So this is when roots repeated twice. If roots are repeated 3 times, for example suppose m1 is equal to m2 is equal to m3, okay, and all other roots are distinct, in this case complementary function is this yc is equal to c1 plus c2x plus c3x square. So here we got 3 constants associated with these 3 roots into e raised to m1x plus c4 e raised to m4x and so on up to cn e raised to mnx. So this is how we find complementary function for real and repeated roots. Now suppose we have complex roots, okay. So the one thing is, for any polynomial with real coefficients, complex roots appears in pair. That means if a plus ib is a root of that polynomial, its complex conjugate a minus ib is also root of the same equation, okay. So we have one case here now, one input here, that complex roots appears in pair. If there is 2 plus 3i is a root of auxiliary equation, then 2 minus 3i must be there. Alright, so we'll need this information. Now suppose, so we have a plus or minus b, this has to be a plus or minus ib, okay. I forgot, so there is a printing mistake. It should be a plus or minus ib are the roots of auxiliary equation. Let us assume this. Then yc, that is a complementary function, will be c1 e raised to a plus ibx plus c2 e raised to a minus ibx. This is that we have studied initially when we got distinct roots. Now this is how we can find a yc. Now let's simplify it. Okay, we know that. So this e raised to ax will be as it is, and for e raised to ibx we can write that as cos bx plus I sin bx plus c2 for e raised to ax, again it is as it is, and for e raised to minus ibx, it is nothing but cos bx minus I sin bx. Now here you can see from the first terms of both the brackets we can take e raised to ax cos bx common, so we'll get c1 plus c2 plus, now second terms from both the brackets we can take e raised to ax sin bx common, so we'll get I c1 here minus I times c2 here. Now because c1 and c2 are arbitrary constants, so c1 plus c2 is some arbitrary constant, and similarly I c1 minus I c2 is also some other arbitrary constants. Let us call this as a and the second as b. So we get yc is equal to a e raised to ax cos bx plus b times e raised to ax sin bx, where a and b are arbitrary constants. So this is how we find yc for complex roots, where a is a real part of those roots. A plus ib you get here, a minus ib, and b is an imaginary part. You get here I times b minus I times b. So yc is a into e raised to ax cos bx plus b times e raised to x sin bx, where this uppercase a and b are arbitrary constants. So I hope you understood this, how to find complementary function when we have complex roots. So no need to do all this calculation here. You can directly write this yc. Let's solve one example. So okay, before that, what if complex roots are repeated two times? So let us consider this case. Now we have a plus ib repeated two times. So in that case, it is same as repeated real roots, because a plus ib is two times and a minus ib is two times. That means there are four roots, so we should get four arbitrary constants. So yc can directly write, it is c1 plus c2x e raised to ax, where a is a real part, cos of bx, where b is a imaginary part, plus c3 plus c4x into e raised to ax sin bx. So this is how we find complementary function for repeated complex roots. So let us take one example. Find complementary function of this differential equation d3y upon dx cube minus 8y is equal to 3x. So its auxiliary equation is m cube minus 8 is equal to 0. So the roots of this auxiliary equation are 2, minus 1, plus or minus I root 3. So these are the three roots, and we got complex roots also. So yc will be, for first root which is a real, we get c1 e raised to 2x plus. Now we have complex roots whose real part is minus 1 and imaginary part is root 3. So a is minus 1 and b is root 3, and therefore we get c2 e raised to minus x cos root 3x plus c3 e raised to minus x sin root 3x. So this is how we can find complementary function for such examples. Thank you.